environmental engineering.
Right. Anyone else? Is that like the right cross section?
We're seniors in mechanical engineering for a capstone project. We were designing a digester for the university's product.
Great. That's super relevant. Anyone else?
Community development and economics.
Great. So we try to do all that, and so what I'd like to do is talk a little bit about the very specific and literal work and problem set that we seek to address with the company, and why we sort of first landed on the technological innovation, and then how that looks programmatically, and then the tools we're trying to use to scale that, to make that actually be able to get to people who need the technology, and some of the challenges of trying to be a small business and not an aid-driven, donation-driven initiative, and then talk a little bit more about the higher level values that we think kind of ultimately drive the work, because at the end of the day, I'd like to sort of discuss the technology and what we do as more of having more power kind of as what it represents in terms of converting something that we widely regard as waste to something really valuable like energy. So I'll run through that, and then some of the specifics. I know that there's a lot of work integrating economics into the ecological systems now, and so we'll just touch on that a little bit on how it means to us, and then hopefully we can leave enough room for questions. And I'll run through a couple of case studies so you can see the type of digestion that we're doing. So broadly, I started in Mexico as a solar engineer, so I was focused more on renewable energies that were a little bit more standard, solar, wind power, micro hydro. And I was introduced to a small digester, actually in Nicaragua, working for a group that was building solar panels with like landmine victims. And so sort of early on really thinking about the cross-section of social justice and renewable energy. And the point really is that a huge amount of people in Mexico, about 42% of the 15th largest economy in the world, still using biomass to meet a large percentage of their energy needs. So that was that came at it from more of a social justice standpoint. These are open fires, three-stone fires. About 2.5 billion people in the world still sort of depend on biomass fuel, and it's a social justice issue related to the amount of time and the proportion of their income that goes into procuring this energy, and also the health risks related to inhaling poor indoor air quality. As we've advanced, we've started to look more at the agricultural sector, and the reality there is that under-equipped farmers tend to have to use more expensive energy, so using gasoline generators, paying really high tariffs in rural Mexico because of long extension lines to their rural areas. So there's a myriad of problems related to the cost and the type of environmental damage that comes from Mexican energy sector, and that's what really, when I saw the first biodigester and I saw that something that they had a lot of, which was shit, could be turned into something that they didn't have enough of, which was clean energy, it was really an appealing project. But we learned really, really early on that the counterpart to a small farmer's life is also the agricultural component, which is right now, in order to stay competitive, and also through government subsidies and sort of business initiatives, a lot of chemical fertilizers are pushed in small farmers to help increase short-term yields, which really both exposing people to a lot of the exposure to the chemicals, but also they're not really used, they're tried to maximize in terms of sales and not really used in balance. So what we have in Mexico is a massive issue related to soil fertility, given that it was one of the first countries in the Green Revolution. So, and the other piece is the broad marginalization of smallholder farmers. So the UNDP just released a report related to the fact that about 70% of the world's food is still grown by smallholder farmers. They're defining those as farmers with under 5 hectares. In Mexico, a smallholder farmer can be quite a lot bigger, and I'm defining it more as a family farm, so someone who isn't like incorporated as a large business, but has a small parcel, grows for a mixture of consumption and sale. In Mexico, that makes up 99% of all the farms, so about 40% of the population live there, and they represent about 80% of the poverty in the country. So providing a massive role in Mexican society, but consistently undermined. mostly through a lot of like massive agricultural conglomerates that are able to take up a lot of land, take up a lot of resources, receive a lot of government support, and a lot of that's for export and things like that. So given that dynamic, as they're trying to grow, they finally have this last challenge, which is a ton of waste. And so as small farms are trying to be more competitive or diversify, they have an issue around growing populations, which is how do you manage animals in these sort of urbanizing contexts when you have a really distinct waste management challenge. So, and all these slides were translated by an intern, so we'll see if the English is actually right. I'm not totally reading them, but so that kind of perfect storm for us led to a really interesting technological solution, which is a small-scale biodigester. So a biodigester in its very most simple form is a container that's completely closed to outside oxygen, where organic matter is fermented in its the sort of simplest term, basically broken down by anaerobic bacteria in the absence of oxygen. So that's a process that's occurring naturally in our stomachs, the stomachs of ruminants, deep in the ocean, in bogs, swamps, and all sorts of areas where you have limited supply of oxygen, and the anaerobic bacteria, which are the original forms of life. They're single-celled, very, very simple bacteria, essentially evolved before there was oxygen, before essentially a massive amount of green plant life on Earth sort of produced oxygen, which drives the more advanced metabolism of us and other animals. So this really, really interesting bacteria is super simple, and it is able to break down, or essentially you can think of it as the extension of the digestive system of an animal. So I'm going to just spend a couple more minutes on this slide to explain, because it's really, really simple, but often people get caught up in some of the mechanics. So at its very basic form, this is like a water level. So it's filled with liquid, and liquid maintains the same, so ignore this first part, but liquid's going to maintain the same level across space. So we can see it's maintaining the same liquid height here. And so what we have is a water truck really similar to what you'd have in your toilet. So as this material goes in, outside air can't go underneath the liquid to enter, and any gas that's built up here is not able to leave. Does that make sense? So it's at a perfect level. And so when we add a little bit of waste right here, so this is, say, a bucket of waste, this puts it out of level, pushes it, and displaces on the other side the same amount of liquid that just went in. So it's not at an angle or being moved along any more than just sort of the constant push. And so technically speaking, who's familiar with digestives besides these like master students in digestion? You, a little bit? Right. So the other probably most important takeaway if you're going to think about digesters in sort of a design concept is the hydraulic retention time. It's a little bit of an oversimplification, but essentially we know through decades of research how much time a bacteria needs to break down different types of waste stream under different temperature regimes. So basically with those three pieces of information, you can design the size of your digester for any given waste stream. And so in Mexico, a temperate climate with a little bit of variation, we use on the order of about 40 days. And so obviously there's a lot of other design considerations that go in, but generally speaking, I want to understand how much waste I have, and then multiply that waste, that daily waste, by about 40 days, considering the water that'll mix in. And that volume, so if I have 1 bucket of waste and I'm going to mix it with 2 buckets of water, I've got 3 buckets a day of volume, I'm going to multiply that by 40 and have 120 buckets sort of as the size of my digester. Does that make sense? And sort of free of units. And so you change that based on sort of tropical or temperate climate regions, but essentially as you think about this, 1 bucket's gone in, it's sitting here on day 1 in early phases of the chemical process. Another bucket comes in, sort of displaces it further. As this breaks down, you're essentially you're first hydrolyzing the waste, mixing it with water, and then you're having different levels of biological and chemical breakdown. So obviously they're physically being separated, and then bacteria breaking down even the most complex solids that are organic, so if you think of like a piece of corn ends up in here, very, very slowly over time the bacteria are breaking it down and its less dense parts are moving along, and so some of the solids will stay in for 100 days, some of the liquid will flow out a little bit easier. And as this builds up, we essentially get a big fermented bubble on the top, and we can send that bubble at low pressure. This is a pressure release valve through a small filter, and we can use that as methane gas. So really similar to natural gas, except instead of being 99+% methane, ours is only about 65 to 70% methane. So the rest is organic CO2 that just sort of comes out in the balance. It doesn't really affect the system. So you do all your energy balance given your known quantity of methane that's going to be in the gas. And so essentially if you think of that in terms of natural gas to methane displacement, if we have 100% methane versus about 60% methane, you need a little bit more volume at the same amount of time to get the same amount of energetic or the sort of energetic potential at any given moment. Does that make sense in terms of like understanding sort of mechanically what we're talking about? This is ground level, so what you'll see in a lot of the photos are these kind of just big domes coming out of the water, or coming out of the ground. They've got corresponding liquid phases down below where all this is happening. And we're essentially only using the transformed digestate, or what comes out the other side, as the seed for the next digester. So the mixture of the bacteria that are already in the cow's stomach mixed with a seed batch from another digester is all that it takes to start this up. And essentially you break off in your chain of evolution, and you, at this point in time, like form your own sort of mixture and population of bacteria. So they'll adjust very, very specifically to the diets of the animals, to the conditions, to the temperature, and they're sort of now evolving in isolation. We have like digesters that are freaks of nature that just have been like overloaded or put under weird conditions and can just like produce gas in really, really strange scenarios. So sometimes if we're having a problem, we'll go like drive 2 hours to like the monster, like the mutant digester, and get some of its sort of bacteria mix to mix with others. And that's essentially how it works. So as a company, as a group, we kind of took advantage of something that was pretty well known. It just wasn't well known in Latin America. And the issues with it becoming well known in Latin America is that basically as a small scale technology, digesters really kind of came to being in the 50s and 60s in China through really top-down government programs and being sort of pushed as a sort of populous rural tool, but sort of done in a very kind of top-down socialist way, installing tens of thousands and having kind of a low adoption, or sort of low percentage of adoption, but it kind of marginalized it as a perceived sort of modern tool for a lot of other people. Come into late 70s and 80s, and you've got sort of the plummeting costs of fossil fuels, and as the technology sort of advancing, it kind of got undermined further. We've been installing anaerobic digesters in the US at waste treatment plants, and really just sort of flaring the methane, not really putting that link together in terms of what this means. So in terms of addressing a series of problems, it's one thing in terms of a more kind of poetic message that we're trying to convey in the work that we're doing. It's really linked to this transformation, something that at its sort of face value is disgusting, completely lacks value in sort of broad social perception, and actually on the contrary presents a lot of risk. There's a lot of health issues here. This is a source of greenhouse gases, a number of other issues related to poor management of waste, whereas a simple intervention all of a sudden transforms that to something that's like really elegant, elemental, beautiful, and has a powerful impact for the people that use it. So like I said, digesters aren't anything new. There's a whole kind of relatively thriving industrial, probably seen these are kind of like generic.
Yeah, we use that picture more.
This one is the one that's like classic. So this is like some sort of generic European industrial vertical, high speed, it gets heated, mixed, has lots of inputs. Probably the pH gets balanced in the feedstock, maybe a lot of pre-treatment tanks before it gets there, but it's functioning under the same thing. You've got a hermetic seal, you've got inflow, outflow, gas capture on the top. The bubbles are sort of just kind of bubbling up here. These are covered lagoon systems, so they're made out of large geomembranes. They're essentially huge covered lagoons. Same thing, it's just like that drawing, but just in giant. And this is like a sort of hybrid of those two strategies. There's also a lot of different types of small digesters. So this is the Chinese dome, or the fixed dome digester that I was referring to in China, made out of bricks. This is kind of attempt at a ferrocement kind of modified septic tank design. This is an Indian floating dome system, so it's just like a fixed dome, but the dome moves, so instead of changing pressure within the system, you have a changing volume. It's just another way of looking at it. And then this is kind of the grandfather of the work that we're doing. It's a cheap plastic kind of interface in a tubular digester, which was a low-cost response to concrete and brick digesters. So essentially what happened to me is that I showed up in Mexico and no one really installed digesters, so I downloaded a manual off the internet of someone who had was like promoting these, and what I got was like something cheap that you can do yourself off the internet for like $50, and that's in the year 2005, so still had to like look for stuff. It was pretty easy, and it's a story I've heard over and over and over again. So I'm in Mexico, so I'm not in the poorest place in the world, but I'm in a place that has a lot of poverty, but a lot of aspirations in terms of what they want to get out of modern agriculture and the types of investments that they want to make. So what we realized is that as we started installing these systems, that really they could last like 5 minutes to maybe 2 years or something, just in terms of like we had some that we'd install, you'd spend a bunch of days, someone would drop a rake on it, a rooster would jump on it, any millions of things could happen, and the sun made it brittle. So it was essentially you're working with a group of people for whom the last thing that they're missing is like extra bit of work in their life or stress or uncertainty. And you're asking them to take a really big risk on a technology which is a massive internal change for them, but you're also doing it with a technology that wasn't reliable. So what we really focused on is taking what I learned after working in the industrial digester industry for a while, which was just you have to have really high quality material, you have to have reliability, and you have to be able to have a business model that actually made sense. So the way that large digester firms function in Mexico today is they try to sell huge amounts of membrane, so huge lagoon digesters. Really, that's their business model is a design charge and selling a ton of membrane. So we realized that we're never going to sell a ton of membrane if we wanted to serve small farmers, so we'd have to make something that was like efficient and scalable. So we essentially developed a bunch of fixed sizes so that and removed the entire design component from it so that anybody could sort of size a digester to a farm's need, really just in a couple minutes by asking a series of questions and thinking about the land and the terrain. And the most important thing is that we wanted this to be a good investment. So we made it out of a material that's the same material that you line landfills with. So it's kind of an inert petroleum byproduct actually, and it will really last like 100 years in the sun. You know, we talk about 10 years in terms of a lifetime, but it sort of will last kind of forever. And then we prefabricate them so that they can be folded up into like tight little bundles and shipped all over the world as it is now. And then they're modular, so people were able to put one in, and then as their farm grew, interconnect it to another. And so modularly, you could make the system a little bit more dynamic and adaptable. We had tons of different sizes, and then we just really focused all our design decisions on something that would be really, really easy to use. So you could probably gain some efficiencies or gain other, like people are always really obsessed with making their digester more efficient. We really realized that the diminishing returns, like almost any container that you close and put waste in, you'll probably be able to digest at like 70 to 75% efficiency. You get in like industrial European digesters with all this heating and stuff, and they sometimes achieve like 85, 87% efficiencies. So that last 10% of efficiency, if it's not really, really functional for the end user. So this was like a really interesting engagement for us. We were able to essentially build a small business, realizing that the entire success of this was kind of based on the return on investment for a small farmer. So we entered with this idea of increasing renewable energy capacity, trying this social justice component, and climate change is kind of our main drivers. And then what we realized is that instead of needing outside funds to push those values, we could make farmers the most important and key stakeholder in the entire process by making the system appealing to them as a purchase, as an investment for their farm. And so everything we do is just completely obsessed with returning investment for a farmer. So whatever they're paying, I want the direct cash benefits that they can see in their hands really clear to them within a year or 2 years of the initial investment that they make. And then we soften that blow by lending them money for about a year to 2 years, depending on that environmental payback. So they're like cash flow neutral throughout the entire process. So you can see here, we've adopted a whole line of small motors, and we're going to be releasing this year a branded line of Briggs & Stratton that will run directly on biogas. So that's a really interesting opportunity for small farmers that live kind of in this either above or below the line of mechanization. So what mechanization allows people to do is pump milk better and cleaner. It allows people to grind animal feed, to grind grains, to do a number of different things just through mechanical energy. And then obviously you can connect those to an electrical generator and create electricity where there's not. So electricity for farmers is refrigeration in the value chain. It's light and the ability to work after hours. Often it's security. So there's a lot of different really important benefits from that. And then the fertilizer piece was really something that we kind of tossed off in the beginning, and now it's actually our main driving point. So we really consider ourselves like our business model is about building soil, and now the energy is the byproduct of that, which is a really interesting way for us as we try to articulate the return on investments for farmers. We talk about the long-term return that they're getting from building their soil over time. And we also talk about an energy balance. So we're all familiar with the last days of ancient sunlight and the idea of burning fossil fuels as sort of banked solar energy that was gathered over time. As you talk to farmers about that concept, it's really, really interesting and apparent to them, and they see. So we've actually been able to help them visualize through where the waste of a cow is essentially, if you back that up the value chain, like run it back up through the cow, that energy came out as milk and meat, and they ate the grains that was harvested from the field, which was a collection of solar energy. So if they have a limited amount of land and solar energy is one of their resources, then they say, like, how do I maximize the amount that I get out of the sunlight that landed on my land? So when they think about extracting the last little bit of energy from this, and then the nutrients go back into the soil, you're essentially keeping energy as energy and nutrients as nutrients, and people see that in terms of an energy balance that they want to live within. And we've essentially created these super vested group of environmental stakeholders. So we kind of at first talking to these like rough farmers, for generations, and we really wanted to like leave our kind of like environmentalism and sort of kind of more hippy-dippy, like sing songs, you have to protect the earth kind of language out of it. We believe that stuff strongly, but it wasn't. We were really trying to make a rational economic argument. And what we found is that these are the conclusions that people come to, and they value it at a very, very strong level. And that actually we've really been leaning into that a little bit more, and people being very, very aware of what they're leaving to their children, and really, really aware of climate change is something that they are seeing and living with in Mexico. We've had the last decade of really not necessarily defined by particularly hot, cold, wet, or dry, but just so varied. So people have their ability to understand the seasons and rely on the seasons and what's going to happen each year is really limited. And then they see that in terms of water, and they see that all interconnected to the loss of forests, so they see that cycle and they see how they're part of it, and that empowering them to sort of break that chain has been has been really amazing because we're creating allies that are often seen sort of at odds with protecting natural resources. Just check that there. So just thinking about the cycle of this, we really, again, like to really think in cycles. Everything starts with the family, but essentially we can convert, if you think about one 20-liter bucket of animal manure, so we just kind of have a back of the envelope. So you can take 20 liters of animal manure, which is kind of the 5-gallon bucket, basically. So if you can put that together, you can convert that into 1 cubic meter of biogas. So a cubic meter of biogas, what that represents is about, a 2-burner stove will use maybe 300 liters of biogas an hour. So that's about 3 hours of serious kind of household cooking. That'll run a 1 kilowatt generator for 2 hours. That would be enough to charge some batteries, run some lights. Or we could basically offset a half a kilo of LP gas. So that translates out to about 15 to 20 kilos a month, which is about what the poorest family would pay in gas each month. And that same 1 bucket of waste will produce 80 liters of organic fertilizer a day, which is the equivalent of enough to offset about $250 worth of chemical fertilizers off of 3.58 hectares, which is about 7 acres, 8 acres of agricultural land. So that in turn, this very, very sort of basic, so obviously we're just using 1 bucket. We've got farms that are using 10 to 15 wheelbarrows of waste a day. So just 1 small bucket, which is a cow or maybe 6 pigs, produces a payback time of about 16 to 18 months if these elements are able to come together. So really interesting cycle. What's spun off of that is not just the inputs, but the independence of them, right? So we really had an interesting breakthrough when we began speaking about this in terms of either using the nutrients that you have here as productive fertilizers, or in Mexico we import all of our fertilizers from Russia. So the concepts of like you are what you eat, and your people are in Mexico are from the corn, which is from the soil, which is why they're strong. So the nutrients of corn pulling up like minerals from the soil creates me and who I am. Now, like the nutrients that I'm pulling up come from like a chemical plant in Russia. It's like a really kind of salient and interesting visualization. Yeah.
So you're pitching it as being beneficial that it produces as fertilizer. Do they not put the manure on the fields if they don't have a digester?
So
I would think you would get more fertilizer than what you started with. Right? It's just going to be easier to haul around.
So they're mixing it with a little bit of water, so you get liquid fertilizer in terms of liters. So the density of this versus what you'd already have. What you're referring to is that you're starting with the same amount of
like the nutrients
manure.
in the manure.
Right. So
they're creating.
right, except that nutrients in manure are not available to plants.
Really?
So they're organic, which means that they're completely locked up. So an organic, like it's like a closed ring. So that's what composting does. So if you do that aerobically, well aerated, you can have a compost heap in about a year transforms those nutrients so they can be taken up. But what you lose is all the nitrogen, which is the key macronutrient in agricultural systems. So all of that volatilizes out as a gas. And so in a digester, the same amount of transformation happens from an organic locked up nutrient. So those are going to be like carbon rings that are holding all the beneficial macro and micronutrients. Those will be converted chemically into something that plants can uptake directly, but you'll retain all the nitrogen. So instead of having like a small amount of nitrogen, you have like a retained chemical nitrogen.
So would it be a simple analogy, say the food's there in the manure regardless, but the plants aren't able to eat it?
Exactly, yeah, it's just kind of like locked up, like you haven't been able to like take them out of the wrapper or whatever it would be. And then the other piece is that year, what really ends up happening, instead of running a productive compost, it piles up. So it gets rained on, most of those like nutrients run into the watershed, so you get nitrification, you get all this contamination of the watershed, contamination of surface water, and the volatilization of that. So the compost is great because you add soil structure and a bunch of other pieces, but it doesn't end up being as potent. So really what our work does now is focuses on like maximizing compost and organic fertilizer, because you can't use generally all the manure from an animal. You really want the clean manure, so it doesn't, you're not going to like run around in a field and try to like collect all the manure, but you will scrape the manure from like a milking parlor or someplace where you have a concrete floor. So we've been now kind of expanding, so we work with small farms. This is a hospital bathroom that we designed in Haiti, so we're receiving all the human waste from the Partners in Health clinic in Haiti. We've worked at slaughterhouses, so that's receiving blood and fine particles of meat from cutting up and killing animals, and all of the manure from their stomachs and intestines. Real pleasant, beautiful stuff, but that all actually, recycling that produces a lot of gas and reduces a lot of contamination. And then the thing that we're really excited about is these really, really small farms, and just sort of where that hits the social justice. So what we really like to think of is we've taken kind of this industrial component, a high quality product, and adapted it to a domestic sector, so it can be really integrated. So this looks like, I'll just show a couple examples. So this guy has a very, very small farm. He has 6 sheep, and they make enough biogas every morning. They like brew a huge thing of like essentially a tole, which is like a corn and flavored drink that they like sell in front of the school every day. And he used to have to do that on wood, and now he does it with biogas. This is another school, so this is human waste coming out of a school with about 300 kids, and so they're using the gas because they cook school lunches there. This is like a small dairy farm, so they run something called, the translation would be like forest pasture.
Silvopastoral.
How do you say silvopastoral?
Silvopastoral.
Of silver, yeah. So yeah, it's like trees, bushes, shrubs, like these intercropped farming. So these guys sell to Nestle milk company, and they run motors, fertilize their entire ranch, and then they use all the excess hot water for producing cheese, and they heat the water to clean all the milking machinery. This is the slaughterhouse. So this is 3 interconnected 40 cubic meter reactors. So basically started with one, and the waste flows between the different reactors, so you kind of maximize the physical retention of solids in the earlier reactors. This is the hospital going in Haiti. This is our kind of new project. It's individual bathroom units with 2 very, very small reactors. And an additional place to put like kitchen straps. So this is for a family that doesn't even have any animals. In Haiti, people spend about 40% of their almost like $2 a day income on charcoal. So just 1 or 2 hours of gas has really proven pretty amazing on top of their sort of sanitation crisis. So this has been pretty interesting work. This is a research center that we have in the Yucatan, so we're testing tons of other waste streams here and a bunch of digesters that are run in parallel. We have translated all of our outreach material into 3 indigenous languages in Mexico, and using that as a way to further sort of drive the assimilation. We've got just past 2,000 digesters in Mexico, and we're in 9 other countries right now, including Ghana, Nigeria, and Haiti, and then the rest are in Latin America. Actually, we have a couple in Cuba. I'm allowed to say that. And so the way that we work, I just want to touch on really quick, and then I just think maybe we can have more of a conversation. So we actually build the digesters, and we mix that with this real strong program of like outreach and impact. So we really try to work with the entire family, working on art and education, and we provide financing through KIVA. So the idea is that through outreach, we get people to sort of, the way that we're presenting this as a larger societal change and agricultural change and energetic change sort of allows digesters at the end of a weekend or at the end of a presentation to be kind of like the the outcome, or like a very logical outcome in a transformation. And then what we're able to do is post each one of these users on KIVA. It's crowdfunded around the world. The average KIVA loan funds in about 3 days. Ours funds in about 3 hours. People are really excited about this kind of cross-section of people. So we've done almost $300,000 of loans through that platform at 0% interest, which has been really amazing. So what I hope kind of comes out of that is that when we think about presenting this change to people, we really kind of come in with this idea that this is a technology that people haven't really heard of. So what we've developed, and it started in the mine communities, was the legend of the new flame. We started, these mines were referring to the digester as a new flame, which to us was like really impactful, like, because it's blue and not orange. And so flame is the original element. And so the idea of like introducing a new flame to an ancient mine community really brought up all these questions, like where would that have come from? We realized that almost all the stories that they talk about, wood, jaguars, pigs, corn, everything had an origin story. So we came up with an origin story for the digester, was this sort of battle between a blue dragon and a red dragon. And from there, we realized that we just ended up launching this whole other way to sort of interact and communicate with people. And so we have like a troupe of people that put on the puppet shows. And basically, through this empathetic outreach, you start creating a space that people are in their own community, but they are more open and receptive to change. And then introducing technologies and things that do that with a proven benefit has been really, really impactful. So, I don't know, I keep trying this. So when the thing that I think kind of that translates maybe to the context a little bit here is that first the value of resources, the way that we sort of look at like nutrient management plans and things as contaminants and not valuing the resource like it can, and the undermining of the small farmer, I think is something that basically was born here and has evolved the most in the U.S. So we're really interested in what that looks like as we try to transfer some of the lessons learned in Mexico to the U.S. and thinking about what that could mean for small farmers here, and hopefully like a growing movement of new small farmers and people that are emerging that would be interested in sort of re-engaging at innovation at a smaller level. So that transformation, that outreach, and like actually caring about a message or something that carries a more broad implication about how conscious people want to be about the work that we're doing in terms of like how we grow our food, how we get our energy, and how we value resources in general. And so I'll just kind of leave with this idea. We, like in this outreach, we've seen over the last 10 years, like our clients and the people that we work with have really like evolved in the way that they think about resources. They feel now that this has kind of opened their eyes to valuing things more around them, being more conscious how they spend money, how they spend energy, where they get everything that they use, eat, buy from. And then we realize that these kids have actually had a digester since they were born. So the kids in this photo will never know a time that animal manure wasn't their primary source of energy, or that their fields were in complete cycle or in balance, or that they grew organic food, and that they were actually sort of independent in that sense. They weren't having to buy energy from the state and dependent on rising energy costs and things like that. So what becomes really interesting to us is the social innovation that like they'll be thinking of as we shift the way that they think about waste and energy. So maybe I'll just leave it there and see if there's more either technical or programmatic questions about what this work pretends to do.
So it was made only out of that black liner that you said you pretty much just dug a hole, and you didn't have to line it with concrete or anything else?
No, we use a trench that has like a specific set of dimensions. So for each for each different type. This is a geotextile. So this is made out of recycled plastic bottles. It's a product in Mexico. I think you can get it here as well. And then this is the geomembrane, which is a high-density polyethylene. And so the digesters come like this, like rolled up in the same geotextile in the back. So the families dug the trench ahead of time, and we just sort of confirm that it's level, and then we just open up the package. And so the liner that is used to protect it in shipping becomes this liner here. And then we just open this up, we make sure it's level, and all you have to do is just glue a couple pieces on. So then you just glue this piece on, you connect it to the pressure release valve, and then this little kid's just filling it with water, so it gains its water trap. And then we seed it with 2% fuel and 10% raw fresh manure, and let it sit for about 30 days, and then it's ready to go.
What temperature do you run it at?
It's ambient temperature, so in central Mexico it gets quite cold. So we run from anywhere from like 12 to 15 degrees in the wintertime, and then up to, in the Yucatan we're running at like almost 40 degrees all the time, which is great. But pretty wide variety.
Is that
Celsius.
Celsius.
Oh, sorry.
No, right, but
Celsius,
is
yeah.
that the external, or is that the internal temperature inside
That's
of
the
that?
internal temperature, yeah. So essentially the temperature balance ends up being somewhere between ground temperature and ambient. And we have a couple of models that do that, but we really, in cold areas, we try to lower the loading rates in the wintertime. And I think we're still kind of dealing with that a little bit. I've done a couple in the US, and my theory, we've had a couple like freeze solid, and then just in the springtime they thaw out and start producing gas again. So everyone in the US spends a lot of time trying to figure out how to heat them all winter long, and I've just sort of been thinking, you just don't use it all winter long, like your swimming pool or something, I don't know.
The one we designed is 15 days.
15-day retention time?
We do have a water heater though to keep it maintained in thermophilic conditions.
It's thermophilic, yeah. So thermophilic is an interesting, it's the theory that at a higher rate, biological output is like faster and more efficient. Mesophilic is the 15 to 40 degrees Celsius range, which is like the range that we all just like pretty much feel comfortable at. It's like what most biological processes happen. So thermophilic bacteria are like way more robust, but if you like change the pH on them or you change the temperature on them a little bit, they kind of like die out because they've evolved under at a vent or at some very specific energy source. Where mesophilic bacteria, we have probably 100 different types working. So like the 20-degree guys kick in sometimes, and then when it like gets colder, the 15-degree guys kick in. So what we're looking for is the most impossible to kill, not necessarily. How many cows is yours designed for? Or this pilot?
Around 150.
Oh, so it's a decent amount. Of like a California full barn style, or?
It's tie style, and then there's like a pack barn pen kind of deal.
Nice.
They're expanding too. There's another tie style. Right. Yeah. So
Great.
2/3 of this tie style.
So I worked initially under sort of big lagoon digesters, and then interconnected generators, like 100 kW generators interconnected to the grid. So that's kind of was like the American model. There's on the order of about 400 to 500 large-scale anaerobic digesters in the U.S. right now at farms, a lot of dairies. But we've started here actually interconnecting like really small, like 5 and 10 kW motors and stuff. So that's been a really interesting sort of move. It's
Are you having difficulty with the hydrogen sulfate on the sulfide?
we use a
Sulfide on the motors.
yeah. We changed the oil a lot, and we have a big sort of 55-gallon drum filter that we designed. It's like coconut
It's gonna
processing,
have a
compost,
yes.
and yeah. So we scrub it about 96, 97%. Get it under 200 parts per million.
What's the biggest obstacle to adoption for these small holder farms?
Generally speaking, it's not necessarily the technology as much as the smallholder farmers, like often on this like constant set of fluctuation, like above water, sort of, so to speak, economically. So a lot of times animals are more like savings accounts. So they'll have like 10 pigs because like life's going pretty good, and they can give them their sort of scrap food, and it's like having a savings account of money. And they'll either keep that in balance or need to cut into it. So a lot of times a very small farmer will come back and they had to sell their cow or sell their pigs or whatever it is because of economic times. So that's tough. And oftentimes it's space. Financial is sort of the easy answer. So we spend a lot of our time figuring out how financing, outside support, things like that can help support these efforts while still sort of maintaining that organic.
So do they come to you, or are you out finding farmers just kind of go out there with a little picture and I don't know?
It's not little; it's a big picture. We're focused in central Mexico, so probably about 80% of our sales are in 3 or 4 states, and we hold weekly 2 or 3 kind of big events, like tents at someone's house. So like these people will install a digester, like 3 months later we'll come back, put a little tent, grill up some tacos, give a little talk, the farmer will explain, he'll invite his friends, he gets a little bonus if any of his friends buy it. And so it's basically taking an unknown technology and sort of having to present it in a way where people slowly over time become more comfortable with it. And so what it is we see that there's like we get an early adoption rate of the early adopters, like whoever they are in their community. They're always the first ones to try something new. And then like a slow and gradual increase as people are like, wow, that worked, and they start making the investment. And then there's like this huge spike where people don't want to be like in the second half of people to have adopted it because they see that, wow, I'm like a sucker. These guys have not paid for gas in 2 years, and I'm still sort of wallowing in manure over here. So we're spending a lot of time thinking about what that tipping point is in different groups.
On one of your slides, you were talking about the return on investment, and it's usually 2 years. Excluding fines, what would some of those fines be?
Oh, so in Mexico right now, so that was actually to make it sound more positive, not negative. Farmers right now that aren't treating their waste are exposed to fines. And so that slaughterhouse was facing a 200,000 peso, so $20,000 fine because all that blood and slop and guts was like going into like a street drain basically. And the digester we installed that had like a 14-month payback or 2 year. What did it say?
2 years.
It paid it back, not including that it only cost him like 60,000, but $6,000. So he saved himself this. Like the time the recuperation investment was massive because he didn't have to pay it out of the fine. Mm-hmm. But independent of that, he still made his money back in 2 years and avoided the fine. So it's like just on regulation alone, all farmers could have one of these or should to avoid that risk. But then it's still a good investment. Sorry.
So if you have a system and it's based on 10 cows and you come back and there's 5 cows, is it lost? Like, is all of that investment, can you retrofit it down? You said you could retrofit it up by adding in a new system. Is there anything you can do to make it function if your input is lessened?
Yeah. So with a closed container, kind of, you'll get the same amount. That's actually almost fine. Like if they go from 10 down to 5, you'll get the same amount of gas from the same amount of manure.
Slower.
No, not necessarily. You'll have a much higher retention time, so the waste will be in there much longer. So if you think about, like, we make up the retention time not because we won't produce any more gas, but it's just like diminishing returns. So if you think of this as the 100% potential to take all the gas out of a piece of manure, and then this is time, we see that it kind of goes like this, and then there's like a really high rate of processing, and then that starts to like level out. So in right about here is our 40-day mark for us. For these guys, they have a higher temperature return. They have a higher temperature signature, so they're at like 15 days because it's operating at a higher efficiency, but they'll have that same sort of plateau where their design has diminishing returns for higher retention time. However, there still are gains, and so if you took 10 cows down to 5, you double your retention time. So you just actually produce a little bit more gas over time for each unit of manure, but you have as much gas as you have, which is the 5 cows.
Okay.
It's a little oversized. It's taking up more space. You paid a little more for it than is optimal at that moment, but it's not something that's not useful for you. I've seen extreme versions of that. Like we designed a farm for 2,000 pigs and came back and they had 10. So that was a little weird. And there was never enough gas to actually even lift up the cover. So I mean that's a couple orders of magnitude. It's a little different.
So is it primarily cows and pigs?
No, we've got a lot of really awesome projects right now. So we have we have guinea pigs, rabbits, sheep, tons of sheep and goat stuff, which has been really interesting in terms of lower water digestion. We have a lot of pigs. We are at a zoo, so we have elephants and hippopotamus, slurry. We obviously have human food waste. We've worked with other agricultural waste. So sort of anything that's reasonably with volatile solids and not too much woody biomass is you can digest.
Are you noticing any trends based on the waste stream, whether it's food or human or animal waste, versus from an efficiency standpoint? Is one more reactive than the other?
Yeah, efficiency is such a slippery term in digestion because it depends on
Biogas
what you're
production.
missing. So yeah, biogas production, you have the highest density of volatile solids. You've probably seen the chart in terms of animal manure produces this much compared to oils and fats and greases.
Yeah.
You just have a much higher level of complexity and pre-treatment that you need. So for me, efficiency would be maybe amount of labor needed to produce reasonable amount of biogas. So really cow manure is super easy. It's been digested 4 times already, and what you have is a pretty stable, pretty consistent. You're not going to get a ton of fluctuations. It's going to work all year round. Versus food is great, but if you put an extra 10% in, or a little grease is in there that you didn't realize, you've made your digester sick if you've designed it tight. Yeah.
So how is the effluent handled? There's probably ranges depending on the farm size, but I mean, you said they use it as fertilizer, so I don't know if they have a manure pit, they spray it like we do.
We have a liquid pit
very
that
different.
it looks kind of like this, but just better structured, and it's an aerobic pit, and then we have a couple different phases in that to try to settle out fibers and stuff, and then generally we're using either small pumps or buckets and distributing it either through drip irrigation or flood irrigation, or actually bucket or sprayer applied. Bigger farms with tractors. We're spending a lot of time on that. We're trying to actually start some fertilizer companies that go around and pull up the effluent from everyone and mix it all together and maybe fortify it with different things for different times of year and stuff like that. So we're really trying to make that value come out.
These farms, are they just grazing only, or do they have barns with cows inside?
It's a mix. We
So
almost
what I'm
they're
getting
all
at is bedding, in the U.S., they'll put a screw press on the end, squish out the solids that have been digested and use that as bedding again. Is that something that you guys do down there?
We're not often. We're mostly dealing with what's left over from grains and straw and stuff that the animals are eating. So not necessarily as much bedding, sand, recycled solids in a